Alright, so what we're going to look at in this section is the last few factoring techniques in this for factoring polynomials. So there are technically two more techniques that we have to look at, and one of them we're going to look at is called the difference of two squares. So what do we mean by this word right here, squares? Like, what do we mean by square? Well, squares are basically, they're called perfect squares for short. We just call them squares. But perfect squares are just, they're numbers that when you square. So for example, 2 squared is what? That's 4, right? 3 squared is 9. 4 squared is 16. 5 squared is 25. And you know, I could keep going, right? But these numbers that you see here, 4, 9, 16, 25, those numbers are perfect squares. So 4, 9, 16, 25, and so on. Those are numbers that are perfect squares. So a difference of 2 squares is when I have a binomial where the first term is squared, so that's going to be like x squared, y squared, whatever, and the b squared is a perfect square, which I've already listed up here. So if you have a binomial like that, if you have a difference, which means subtraction, of a variable squared and a perfect square, then you can factor it. And the factors are just going to be a plus b and a minus b, and that's it. And it's pretty, you know, other than that, it's pretty simple to factor it. So if I look at these examples right here, right, this is a difference, right, because I have a subtraction. The first variable is squared, and 49 is a perfect square, right? If I kept going with this list, 4, 9, 16, 25, the next one would be 36, the one after that would be 49. And that's, so 49 is a perfect square. That's the number 7 squared, right? So this means I have a x squared minus 7 squared, which could be written as x plus 7 and x minus 7. So if I were to write this in the form that's up here, this is just x squared minus what number squared gives me 49? 7. So this just factors to be x plus 7, like this, and x minus 7, like this. That's it. So, you know, that one's easy. So if I look here, well, I already know that 36 and 25, so 25, the next one, like I said, is 36. They're perfect squares. And the w squared and y squared are also squared terms. So I could write this as something squared minus something squared, which is a difference of 2 squares. So 36 is 9, and w squared is just w. 25 is 5, and y squared is y. So because I could write this expressed as this form, right, as a difference of 2 squares, these are the terms that are squared to get me the original binomial. So I could write this as a minus b, or I'm sorry, a plus b times a minus b, which is going to be 9w minus 5y times 9w plus 5y. And that's it. That's how you factor a difference of 2 squares. A difference of 2 squares. So let's look at this one. Now, if you notice here, this is not a difference of, yes, it's a binomial, It's a difference, but it's not perfect square. All right, 4 is a perfect square, and so is 36, but the variable here is to the third power. It's cubed. And the variable here is to the first power. So this is not a difference of squares. So how am I going to factor it? Well, remember, the first thing you should do is factor out a GCF. And I haven't been doing that deliberately because there was no GCF there. So let me factor out a GCF. So what's the highest factor between 4 and 36? Well, that's 4. And what's the highest factor out of x cubed and x? X. So I could factor a 4x out of the whole polynomial. So when I factor a 4x out of 4x cubed, I have x squared left over. And when I factor 4x out of negative 36x, I have a negative 4 out of 36 is 9. X out of x is, well, that's 1. So that's what I have factored out of there. Alright, so when I factored the GCF out of here, this is what I have left over. Now, remember, just because I factored once doesn't mean I'm done factoring. This right here ends up factoring. This is a difference of 2 squares, right? It is. It's a difference of 2 squares because I have x squared minus a number squared. 9 is a perfect square. It's 3 squared. So I could represent this. So this right here factors to 2 factors. X minus 3 and x plus 3. And that's it. That's it. Because this right here is a difference of 2 squares. 9 is a perfect square. Okay. So, you know, when it comes to differences of 2 squares, you know, so this will factor to this and this. That's really, you know, when it comes to differences of 2 squares, that's pretty straightforward. Now, I do have to mention something here. This is important to understand, but there is no such thing as a sum of squares. In other words, this does not factor. Like x squared plus 25. That's a sum of 2 perfect squares, but that does not factor. This is prime. You know, same thing as x squared plus 16, x squared plus 36, and so on. These are all prime. They do not factor. So that's important to understand. A difference of squares factors, but a sum of squares does not factor. Now, as we move on to cubes, right? As we move on to cubes, the sum or difference of 2 cubes. So this is if I have a term to a third power. If I have a binomial to a third power. Now, there is such thing as a sum of a cube and a difference of a cube. When I'm dealing with cubes, I do have a plus and minus variation, so they both do factor. And they factor to the following terms. So I get a binomial and a quadratic term. I get a binomial and a quadratic term. That's what this is right here. This right here, that's a quadratic term. In both cases. So if you have a sum or a difference of a cube, you're going to get a binomial and a quadratic term. This one, I mean, it's not too bad when you practice it. Once you recognize you have a perfect cube, so that's what we mean by cube in this case, then you could see if it could factor it. So a perfect cube is when you have a number to a third power. So for example, 2 to the third is what? 2 to the third is, that's 2 times 2 times 2. So that's 8. What's 3 to the third? That's 3 times 3 times 3, which is 27. 4 to the third, that's 4 times 4 times 4, which is 64, and so on. So these numbers right here, 8, 27, 64, and so on. Those numbers, I could keep going on. Those numbers there are perfect cubes. So if you see a perfect cube in a binomial somewhere, and the first term is cubed, then you possibly could factor it. So, you know, in this example right here, I have x cubed, right? Plus, and I just got done saying 8 is a perfect cube, which is here. So that's going to be 2 to the third power. So this factors. What does it factor to? Well, if I look at the form, I have a sum of cubes. So I have a plus b. So I have x plus 2. And then the quadratic term. So I'm going to have a squared. So this right here is the a. So that's going to be x squared minus a times b. So this is the a and this is the b. So that's going to be minus 2x. Right? And then I have plus b squared. And this is the b. So if that's b, which is 2, then that number squared is 4. So this factors to those two things. This is a binomial and a quadratic. Now remember, quadratics also factor, don't they? I mean, they could, and sometimes they don't, but we still have to check and see if this factors. This is a quadratic. So we have to factor it with the AC method. So since the leading coefficient here is 1, or if you remember from the AC method, that's actually pretty easy. So the leading coefficient here is 1. So let's just write this down here. So my factors of the leading coefficient are 1 times 1, which is fine, and my factors of 4 are 1 and 4 and 2 and 2. So remember, because my leading coefficient is 1 here, I don't have to write duplicates for each pair. I could just write one of them. So this is going to be that pair and this factor. So this is x and x in both cases. This is 1 and 4, and this is 2 and 2. Alright, so what I want to do is I want to find the outside-inside combination that gives me -2. Now if I look here, that outside, that inside, that's 4x and x. Is that going to give me -2x? No, it's not. That's not going to give me -2x. What about this outside inside? That's going to be 2x, 2x. Is that going to give me -2x? No, it's not. No, it's not. So what does that mean about this quadratic? It's prime. It doesn't factor. That doesn't factor. So because that doesn't factor, this is it. I'll just rewrite the factored form here. That's as far as you can go. That's it. So yeah, just because this didn't factor, it is a quadratic, and you still have to make sure it does factor. That's important. Don't assume that just because I factored it like this, I'm done. You have to make sure that these other factors don't also factor. And I checked it. I've exhausted all the possibilities. So since none of them work, since none of them give me the middle term, this doesn't factor. So that's it. X plus 2 times x squared minus 2x plus 4. Those are my factors of this sum of cubes. Okay, let's go to the next page. So if I look at this example here, now again, 64 and 27, those are perfect cubes. T is to the third, W is to the third. So this is a sum of cubes. Okay. In other words, it could be written like this. So what number cubed gives me 64? Well, this is a perfect cube, right? So 4 to the third power gives me 64. So that's 4. And T is to the third power, so this is 4T. Now what's this term? So what number? So 27 is a perfect cube. So 3 cubed gave me 27, and I have W. So my terms are my A is 4T and my B is 3W. So if you look back to the previous page, right? It's a sum of cubes, right? So it factors to be A plus B times A squared minus AB plus B squared. So my terms were 4T and 3W, so this will be 4T plus 3W, all right? So the factors are 4T plus 3W, all right? That's my A minus B term, right? And my next term is, I'm sorry, this is A plus B. My next term is going to be A squared minus AB plus B squared, right? Because that comes from the sum formula for the sum of cubes. A squared minus AB plus B squared. Alright, so this is A, so A squared is going to be this term squared, which is 16T squared, minus AB, this is A, this is B, so if I multiply them together I get 12, what? I get 12WT. And then B squared, this is B, so that squared is 9W squared, plus 9W squared. So this sum of cubes factors to this times this. Now, if you remember from the previous section, right, let me get this for you. This right here is a quadratic, but specifically it's what? That's a quadratic in 2 variables. That's a quadratic in 2 variables. Remember this example from the previous section? You see how they're kind of related a little bit? So this right here and this right here, they're quadratics in 2 variables. They kind of look similar. Like I just wrote it here, right? This is a quadratic in terms of x and y. This is a quadratic in terms of w and t. So they look similar in structure. But this is the example from the previous section. That was a quadratic of 2 variables. Here's the same kind. It's the same kind of quadratic. So you have to see if this factors using the AC method, just like we did with this one. We have to list out all the possibilities to see if it factors. Now, I'm not going to lie, to see if this one factors, there's going to be a lot of cases. So, because this is a quadratic in terms of t, right? So here's the a coefficient, here's the b coefficient, and there's my constant. So what are the factors of 16? Well, I have 1 and 16, 2 and 8, and 4 and 4. What are the factors of 9? Or in this case, actually, what are the factors of 9w squared? So again, to do this, just focus on the number and then we'll tack on a w for each one. So the factors of 9 are 1 and 9 and 3 and 3. Now because this is w squared, I have 1w, 9w, 3w, and 3w. So here's a pair of possibilities. Here's a pair of possibilities, and here's another pair of possibilities. And then you would take those three and check this pair as well. So here's another pair of possibilities, another pair, and yet another pair. Now, that seems like a lot of possibilities, but you're going to have some duplicate pairs because I have 4 and 4 here, and I have 3w and 3w here. So some of the pairs are going to be extra pairs. You could just get rid of them. So let me list out the possibilities here. So the first pair is going to be what? I'm going to have a pair here and a pair here, right? So this pair right here, so I have t and 16t, right? t, 16t, t, 16t. And that's going to be for w and 9w. But then I'm going to flip it. So that's going to be 9w and w. So this right here corresponded to that pair right there. Now I want to look at this combination. I forgot to put another set here, sorry. So this combination is going to be t, 16t. Right? And then I'm going to have 3w and 3w. Oh, but guess what? My video froze, hold on. Guess what? If I flip 3w and 3w, what is that? Still 3w, 3w. So remember how I said you're going to have duplicate cases? Well, here they are. So this is t and 3w, 16t, 3w. t, 3w, 16t, and 3w. So I have a duplicate case. So in other words, I could get rid of one of them. Okay. So that was this. So this right here is for these two, and this right here is for these two, but I don't need both of them because one of them is just, it's a copy of the first, it's just a copy. So now let's go on to this one. So now I have this is going to give me a pair, but then I'm going to have another duplicate. So really I only have 3 here. So 1, 2, 3. All right, so this right here is going to be, so this is going to be 2t and 8t. Right? And then that's going to be 2t and 8t again. So the first pair is going to be for w and 9w. And then I'm going to flip that. So it'll be 9w and w. Now I have 3w and 3w. Now again, I don't have to write another pair here because that would be another duplicate case. I'm not going to do that because that would just be, redundant. So those are the 3 I have to consider. Now let's go to the last one. And look at this. The last one actually is another duplicate case. So when I write down 3 more, so this is going to be 4t and 4t, 4t and 4t. So this is W, 9W. But then if I flip that, and I have 9W and W, what do I have again? I have a duplicate case. Here's the 2, here's the other 2. So actually, because of this duplicate pair, I have another one I don't have to care about. I can get rid of one of these. And then finally, the last one is 4W, or I'm sorry, 4T, 4T. And then 3W, 3W. Now I obviously don't have to flip that because that would just give me the same thing again, just like I had here. I would get another duplicate case. So when it's all said and done, all the possible factors for this polynomial are 1, 2, 3, 4, 5, 6, 7, 8. So there's 8 different combinations that might give me negative W, or I'm sorry, negative 12W. If one of these combinations gives me negative 12W, I have my factors for this quadratic. Alright. Well, guess what? If I go through all of these, so if I go the outside, inside, if I go through all of these, none of them are going to give me negative 12W. How do I know that? Because I've done it already. And just to save time, if you check that, just like I did with the example in the previous section, right? If we go to the outside, inside, if you check that to get you the middle term, right? So here, like when I did it here, this one gave me the middle term 13xy, which is what I needed. But if you go through that in each of these cases, none of them are going to give you negative 12WT. You know, if I look at this one, right? That outside, inside, so that's 9WT, right? The inside here is 16WT. Can I get 12WT from that? No. That's going to give me 25 or I can't get negative 12 from that, so that won't work. So that one's no good. And if you go through all of them here, you'll find that none of them work. So guess what? This ends up being prime. A lot of work. That's a lot of things to check to see a factor just to find out that this thing doesn't factor. But you still have to check to see if it doesn't factor. I'll say this. This one's a challenging one. There's a lot to it because it's a quadratic in 2 variables, and not only that, but it's a quadratic that has a lot of cases you have to look at. This one's a challenging one. I will say this one's a challenging one. But so I'll just say here, none of these factors give negative 12t. So 16t squared minus 12wt plus 9w squared is prime. So yeah, I know it seems like a lot of work, so none of these work. You cross all of them out. But you still have to check to see if it does factor. So this sum of 2 cubes only factors to be this and this. Those are my factors. So yeah, that one, that one was a challenging one because, you had a variable, you had a quadratic and two variables, and you had a lot of cases to consider. But as long as you take it one step at a time, you'll be fine. Just look at each pair, consider each pair. So here's a pair, 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 here's a pair. And any duplicates that arise, get rid of them. And then just check to see which ones give you the middle term if it exists. It doesn't exist here, that's why this doesn't factor. Okay, so that's it then. Alright, so guess what? We have seen all the different methods that you would need to factor a polynomial. Now, there are things that you'll see in college algebra that are more powerful. Like you'll see things called the binomial theorem in college algebra. We don't look at that here, but those are the most basic forms of factoring that exist. So if you're given any polynomial, how do I factor it? Well, the first thing you should do is factor out a GCF. So from here on out, if I ask you to factor something, the first thing you should consider is if a GCF exists. And if the leading coefficient is -1, just tack that with the GCF. If it doesn't, or if it does and you factor it out, then you got to see, all right, is there a binomial? And if so, does it have a special form? In other words, is it a difference of two squares? Or is it a sum or difference of two cubes? Just like we've seen. If it is, then you could factor it. If it's a quadratic, which looks like this, it could look like this, it could look like that. You want to factor it by the AC method using trial and error or by grouping. Either one works fine, or you could just use trial and error or grouping. Either one is fine, but you have to see if you could factor. Just like I did here. This was a quadratic in two variables, so I had to see if it factored. Just like this was a quadratic, but this was a basic quadratic in one variable. I had to see if it factored with the AC method. It didn't, so that was it. And the other strategy we looked at is if it's a four-term polynomial, we factor by grouping. So those are all the strategies we looked at. You want to apply them until the polynomial can no longer be factored. At which point you're done. So again, you may have to factor a quadratic or any polynomial in general. You may have to factor it several times. It could take 3 or 4 times to factor it completely. It just depends on how sophisticated the polynomial is that you're trying to factor. That's really what it comes down to. I won't lie, this one was a pretty challenging one because of what it became. But, factoring is something you have to practice at to get good at. There's just no way around it. So to summarize, let's look at these polynomials here. So with these 3 examples, we're going to apply all the strategies we learned with factoring. We're going to apply all of them. Okay, so what's the first thing I should consider? Does a GCF exist here? Well, it doesn't, no. But how many terms does it have? It has 4 terms, so you should consider grouping. So I'm going to do that. I'm going to use grouping. All right. Here's my first group. Here's my second group. So what's the GCF in the first group? Well, they have a x cubed in common, it looks like. Yeah, so they have an x cubed in common. We'll factor that out of that group. Now, what does this have in common? This has a, well, they have a 1,000 in common, right? And it's going to be positive because it's positive in this group. So that's going to be plus 1,000. What's left over? Well, x cubed out of x to the fourth is x. X cubed out of minus 2x cubed is minus 2. If I factor 1,000 out of 1,000x, I have x left over. If I factor 1,000 out of minus 2,000, I have what? Minus 2 left over. Hey, look at this. That has an x minus 2, and this has an x minus 2. So I can factor this x minus 2 out of each term in the whole thing. So I could factor that out of this, which is x cubed left over, and I can factor this out of here, which is plus 1,000 left over. All right. Am I done? Am I done? I'm not done, actually. What's this right here? That right there is a sum of 2 cubes, because this could be written as a number cubed plus a number cubed. The first one's easy, that's x. What number cubed gives me 1,000? 10. So this right here is a perfect cube. So that factors. What does it factor to? Well, what does perfect cubes factor to? Right here. So it factors to this and this. So that's a plus b. So this factors to a plus b, which is x plus 10. And it factors to a squared minus ab plus b squared, which is going to be what? So a squared, right, is going to be x squared minus, right, ab, which is x times 10, which is 10x plus b squared, which is 10 squared, which is 10 squared is 100. So this sum of 2 cubes factors to be x plus 10 times x squared minus 10x plus 100. Now what is this? That's a quadratic. Does that factor? I have to see if that factors, right? So if I go up here, right, so this, the leading coefficient here is 1, so that's 1 times 1. What are the factors of 100? 1 times 100? 2 times 50. 4 times 25. Anything else? Yeah, 10 times 10, right? Or what about 5 times 20, right? Anything else? Yeah, 10 times 10. Okay. So, since my leading coefficient here was 1, I only have one factor of each case. So this one is a case, this one is a case, I have 5 cases, right? So this is x 100, x 250, x 425, x 520, x 10. Are any of these going to give me the middle term, which is negative 10x? So this is 100x and x, that's 99x, that's not it. This would give me 48. That would give me, what, 25 minus 4 is 21. That would give me 15, right? 20x, 5x, that's going to be either 15. That's either going to be 15x or 25x. That's not going to give me negative 10. And 10x, that would have to give me 20x, right? But I have negative 10x. So none of these are going to work. So what does that mean about this quadratic? It's prime. It doesn't factor. So since that doesn't factor, this is prime. None of these work. None of them work. So because that's prime, this doesn't factor. So this sum of cubes only factors to these two right here. So the factors of the whole thing, right, I just have to tack this on to this, and then I have all my factors. So my factors are this, x minus 2, and these two, because this factored to be this and this. X plus 10 and x squared minus 10x plus 100. Those are my 3 factors. So this 4-term polynomial factored to be x minus 2 times x plus 10 times x squared minus 10x plus 100. None of these factors factor any further. This was a quadratic, and we went through it and we found out that none of them work, so this is prime. It's not going to factor. But you still have to check it. You still have to check it. Okay, let's look at this one. Does it have a GCF? It does. It's 3 terms, so it's not grouping. So let's factor the GCF out. So what is the GCF? Well, the highest factor between 10, 15, and 40 is going to be what? Looks like it's going to be 5 to me, right? And then they all have a power of what in common? They all have a power of x in common. So if I factor that out of there, what do I have left over? So 5 out of 10 is going to be 2. X out of x squared is x. Five out of negative 15 is negative 3. 5 out of 40 is 8. X squared, right? Because x out of x cubed is x squared. Now, what's wrong with this? Well, it's not written in descending order, right? When we write a polynomial, we write the powers in descending order. I could have done that up here, but at some point you have to write it in descending order. So let me just rewrite this as 8x squared plus 2x minus 3. So now I have this. And if you notice here, this is another quadratic. So let's check to see if it factors. So the factors of 8 are 1 and 8, 2 and 4. The factors of 3 are 1 and 3. So here's a pair, and here's a pair. Alright. There's a pair there, and there's a pair there. Okay. So 1 and 8, that's going to be x and 8x, right? 1 and 3, and 3 and 1. Alright. 2x and 4x. 1 and 3, and 3 and 1. Okay. So I just got to check to see which ones are going to give me positive 2. So what's the outside, inside here? So x and 3, that's 3x. 1 and 8 is 8x. Can I get positive 2x from that? No, it doesn't look like it. No, because in order to get, 8 minus 3 is 5, and 8 plus 3 is 11, so that's not going to work. What about this one? So that's x. This is 24x. No, that doesn't look good either. This one, that's 6x. That is 4x. Am I going to get 2 from that? Plus 2x from that? Possibly. How would that have to work? So in order to get plus 2x from that, this would have to be plus 6 and 4x, right? So in order for this to be plus 6x, the plus is going to go here, right? The minus 4x is going to go there, right? Now, does that work? The last thing I have to check is see if the last term works. So negative 1 times positive 3 is negative 3. Yep, so that's it. That works. So this does factor. So this factors to be what? So I have 5x sitting out front from the GCF. And my two factors of this quadratic are 2x minus 1 and 4x plus 3. That's it. All right. One more example. GCF, yes or no? Yep, there is. What's the GCF between 50 and 8? Little reminder, how do you do that in your calculator? Go to Math, go over to NUM for number, and go down to GCD. Hit Enter, type in 50, 8. 2! Just a little trick in your calculator. I've already showed you that, but just to remind you. Do they have any T's in common? No. Do they have any W's in common? Yep. How many? 2. Alright, so let's factor that out of there and see what we have left over. So 2 out of 50 is 25. W squared out of T squared W squared is T squared. 2 out of negative 8 is negative 4. W squared out of W to the 4th is W squared. Alright. Am I done? No, I am not. What is this right here? That's a difference of what? That's a difference of 2 squares. How do I know that? Well, because 25 and 4 are perfect squares, and T is squared and W squared, and it's a subtraction. Remember, a sum of squares doesn't factor. So if this were a plus here, I'd be done. So what is a difference of 2 squares factor to? That's easy to remember. That's just A minus B and A plus B. So 2W squared. In other words, this could be written as what? Something squared minus something squared. What are these things in here? So what number squared gives me 25? That's easy. 5. And I have t there, right? What number squared gives me 4? 2. And I have w squared, so that's w. So my factors are the following: 5t minus 2w and 5t plus 2w. And that's it. None of these factor any further. That's it. So again, just to illustrate, just to illustrate the concepts of factoring, the best way to factor is to practice. Practice, practice, and practice. But to summarize, the first thing you should do is see if you can factor out a GCF. Always see if you can factor out a GCF. And then see if any sums of or differences of cubes or difference of squares exist. If you have a quadratic, do the AC method. If you have 4 terms, do factor by grouping until you can't, think of anything else to factor, or until you can't factor it. So yeah, that's a summary of factoring, which you will get better at just as we go along. So the last section in chapter 6, which is 6.7, we're going to actually start solving polynomial equations. So what happens when we set these things equal to something? We haven't looked at that yet, and that's what we're going to look at in 6.7. So that's the end of this video.